Okay, so for the test tomorrow, obviously you need to know Newton's universal gravitation equation. Okay? G obviously is the universal gravitation constant. It is, and it's on the sheet if you forget. Okay? Yes. I'll put red stars next to the things that are not on there. All right, now. From here, one of the things, we were able to derive two equations. These two equations are not on your sheet. Oh, okay, so three. I wasn't thinking of that, although I do have it written down here. You ought to be able to use this to calculate the acceleration of gravity on a planet, right? Because my force of gravity, or the force of gravity on me on this planet, is due to my mass and the Earth's mass, right? So to find, how do we alter this to make it the acceleration of gravity on a planet? You divide by your mass, so this becomes, so the acceleration of gravity on a given planet would be G times M, where M is the mass of the planet over R squared, where R is the radius of the planet. Does that make sense, you guys? All right, now that's not on the equation sheet. Ideally, you'd be able to derive that easily just by realizing, oh, well, I just divide by the mass, right? Okay. Similarly, we learned, oops. That you can calculate the velocity of an object traveling in a circular orbit by taking gm divided by r and square rootifying it.
And r is from the center of gravity of the object.
R is the orbit, yes, center of the planet to the orbit.
And m is the
mass of the planet being orbited. Yeah. And that's in general, you guys. All of these capital R's mean from the center of the planet to the object, and capital M is the mass of the planet or sun or whatever.
Yeah.
Okay?
Or black hole.
Correct.
Or neutron. Or that. Or that.
Escape velocity. All right, and in the notes we derived these, so I would review those. Cool. From this circular equation, oh, that's not what I wanted to do. I heard somebody balk and derive it. Should I talk about that real quick? Okay. It's basically just, if you set this equal to mv squared over r, you can rearrange it and get this. Okay? All right. Oh, from this you can generate an equation for period. So the period, oops. So the period of an object in circular motion is, I always forget it. I always derive it usually. Let's see. Did I write it? It's 4 pi square root of gm over r cubed squared. Is that right?
Is that pi squared?
It's pi squared.
Oh, it's pi squared.
Yep. Okay. Good. Sorry, I did this in my head. Let's see. Oh, you're right. I gotcha. Yes, thank you. It is 2 pi because I took the square root. My bad. Sorry. I knew something was funny there. Okay, so anyway, so here I obviously don't have this memorized. So where does this come from? Well, look, V circular is just 2 pi r over t. So if you replace this with 2 pi r over t, and then solve for t, it gives you this or something really close to this. Okay? Cool? All right, I apologize. I apparently stopped like half a step too early when I was writing this down. Okay, so are we all good with that? Cool. And most of these problems are just kind of plug and chug. I want to encourage you to sort of be familiar with making those sorts of substitutions and working the algebra. Okay. All right, so energy. Here was the thing. A student was in after school on Friday, and it became apparent that I had not done a great job making something clear, and I want to clarify that right now. Okay, so check it out. Gravitational potential energy. We learned the equation for gravitational potential energy was this, right? Okay, and we learned that the equation for total energy was negative GMM over 2A, where A was semi-major axis, right?
Not from the center to like the elongated part?
Yes, correct.
Like that.
Yep. Okay, and then there was this sort of discussion about whether or not, when you could use these for circular orbits and when you could use them for elliptical orbits. And I think I did not do a great job explaining that. So, the gravitational potential energy at a given point depends on the radius at that point. Does that make sense? Right, because the farther you are away, the more gravitational potential energy you're going to have, right? Okay? One of the things we learned was that the total energy depends solely on the semi-major axis. Well, and the two masses, right? Okay? I think the thing that I did not do a great job painting, and I think this might be part of the reason that you guys struggled with the X credit, is the kinetic energy thing. So, only if it's a circular orbit is the kinetic energy equal to negative U over 2, which is what? G times M. Oops. All right, and I think I did not do a great job explaining that this equation was only true if you were in a circular orbit.
So you can't just substitute A in.
Correct. So let's think about why. First of all, your kinetic energy as you go around the circle changes, right? As you go around your ellipse, it's going to change, right? Because think about it. This is the sun, and this is, a planet or something going around it. The velocity is going to change, right? Okay? So if you replaced this with A, that would be equivalent to saying that the kinetic energy was always constant. Okay? So you've got So I guess what I would do then is, so your safety net is just remembering that kinetic energy is 1/2 mv squared. That's always true. Follow? Okay. So everything there that I wanted to, I think I did. Okay, so I think this is a good time to take a quick break from going over the equations and run through the extra credit, which I think you guys will be like, oh, that makes sense. Are there questions on this before I do? Marcus, you okay?
Yeah, I just kind of lost it.
I gotcha. If you want to move up, there's an empty seat here. I don't know if that helps any. Or I can make this maybe not so small. What were you trying to reach? Bottom? Oh, you have your glasses. Okay, so are we good or no? All right, so the extra credit. So here's the deal with the extra credit. What we were given was, you were given the radius of a planet and the launch distance, and you were asked what the minimum velocity would have to be to get the thing to stay in orbit, right? Without hitting the planet, right? And so the drawing that we made was this. We had a planet that had a little radius. Oh, shoot. A minute ago I said capital. Oh, no, this doesn't contradict that. All right. So you've got little r and then big R. Good? So your orbit is going to look like this, and we want it to just sort of like kiss the planet there, right? And just barely miss it, right? Okay? So what we know is that A is, well, how can I use this information to find A, you guys? Yeah, it's the distance from the center to the outer edge, right? Well, isn't that just half of R plus R?
Yeah.
Right? So A is 1/2 of R plus R, right? Okay, well remember, that determines our mechanical energy, right? So that means that our E is G M M over A, where A is this mess, right? So that's 2G M M over R plus R. All right, is everybody okay up to there? All right, now what we need to do is we need to make sure that at our launch point, we give the thing enough kinetic energy so that when I add my kinetic energy plus my potential energy, I get that number, right? Does that make sense? So I want 1/2 mv squared plus, let's see, the potential energy at this point. Oh shoot, sorry, I forgot to make it second, didn't I? My potential energy here ought to be G times M over what? You guys tell me. Big R, right? And it's negative, right? So that's got to equal this. Yeah, Francis.
Your green equation is for the right side only. You also make the thing because negative G M M over R is for potential energy, but you also have kinetic because you're on that side as well.
Did I forget a 2 in there? I did, I forgot a 2. Sorry. Sorry, I did. Oh, no, wait. Yeah, this should be over 2A. Gotcha. Damn it. Yeah, this should be 2A. Right. Look at my notes. Chicken scratchy notes that we've got. So, sorry, let me clarify what I just did there. So, yes, you would absolutely be moving, 100%. But one of the things that we learned was that your mechanical energy, once you've got your thing in orbit, any kind of orbit, elliptical or circular, the total mechanical energy is this equation, negative G M M over 2A, where A is the length of your semi-major axis. Okay? And so the idea is this red shape tells me my semi-major axis, right? Okay. So I forgot the 2 when I wrote it down, so that was my bad. All right. Are we good or no? Francis, are you set? Is everybody set? Good. Okay, cool. So from here we can solve for phi, right? All of the m's cancel out. Lowercase m's, I should say, cancel out. So I want to add this to both sides. So I'm going to get 1/2 v squared equals, if I add this to both sides, you get gm over r minus gm over r plus r. You guys can do the algebra from there. So if you keep simplifying it, you end up getting v equals the square root of 2gmr over r plus r times capital R. So a lot of people had an answer without the r and the capital R there. Yeah.
So that gives you the velocity for if you're like already in space to establish an orbit.
Mm-hmm.
If you're doing it with escape velocity, could you just add the two vectors to a vector for the kinetic energy?
Wait, rewind and say that again. Let me
If you-
interject why I stopped you. So as soon as you go to escape velocity, you're not going to be in orbit.
Sorry, let me rephrase that. If you want, yeah, if you want to go going directly from a planet's surface versus already in space, would this work as well?
Yes. So what that would equate to is, I see what you're saying. Gotcha. So there, what you would have to do.
That would be an issue of like the path you take leaving.
Well, no, because gravity is a conservative force. So the path that you take to get out to your orbit radius shouldn't matter. So the idea is, on the planet's surface, all of your energy would be gravitational potential energy, so G_mm over little r. And then you need your total energy to get up to this. And so the difference would be how much energy you have to gain in, which presumably would be attained by giving the object kinetic energy to start. Does that make sense? Okay. Good, you guys? All right. Questions on this? Okay, so which equations that we used here are not on the sheet? This guy's on there. This total mechanical energy equation is not. This kinetic energy equation is not. The regular kinetic energy equation totally is, I assume, right? Where did I put the equation sheet? 1/2 mv squared.
For the total mechanical, if it was a perfect circle, it would just be the radius of the circle, right?
Correct. Correct.
Two?
Sorry?
No,
With the two.
A instead of this.
Yeah. Yeah, because when you've got a circle, if you think of a circle as an ellipse, then the length of your semi-major axis is your radius. Cool. All right. Other questions on that? All right. So, and then I think the only other kind of general thing that I would, I guess, call attention to is making sure you have some kind of general semblance for Kepler's laws, right? That the object being orbited is at one of the foci, right? What's at the other focus? Just empty space, or maybe some other part of the planet or something, right? But nothing special. Make sure you remember that when are you moving faster? When you're farther away from the thing you're orbiting, or closer? Closer, right? Okay. And remember, Kepler stated it as the planet sweeps out equal areas in equal times, right? What's the sort of more efficient way of stating that? Conservation of, you're really close. Angular momentum. Okay? So the angular momentum at any given point is going to be constant. All right? Now, calculating the angular momentum at here and here is easy because your velocity is perpendicular to your radius, right? Follow? Right? So it would just be velocity 1 times radius 1 equals velocity 2 times radius 2, right? Right? The masses are going to cancel. Will that work at any point in the orbit? No, because at other points, remember, angular momentum is m times r cross v, right? So if you pick some random point, if I go, say, here, there's my radius, there's my velocity, they're not perpendicular, right? So then it gets ugly. So what should I be thinking about then to calculate the velocity here? That was central to what we just talked about here. What was the whole premise behind this solution? Conservation of energy, right? So the idea is here, I know that my total energy at any 2 points ought to be equal, right? So I ought to be able to use that to find the velocity at a given point, right? Because to describe the point, you'd have to know your radius, so you can find your gravitational potential energy. Follow? Okay. And then Kepler's third law is that the square of the period, oops, try that again. The square of the period is proportional to the radius cubed. Cool, where this little alpha here is proportional to. Do you guys prefer the little wavy line?
One is big R.
Average radius. Yeah, so for Kepler, he was speaking in terms of averages. So the period squared is proportional to the average radius cubed.
So the average distance that an orbiting object is away from it.
Yeah. Yeah, now that you say that, that's interesting that this is the way it's always written in books. That's A. That average radius is just your A. So I don't know why it's not written that way now that you say that.
It is. Oh, yeah. So it's just A cubed.
Yeah. All right. So, in my mind, those are kind of like big ideas. Okay? So the way the test is set up right now, and I'm not quite done writing it, but as of this moment in time, it's 15 multiple choice questions and then a pretty easy FRQ. Okay? Oh, speaking of, shell theorem. Shell theorem, there's not really an equation for it, but if you've got an object out here being attracted to a planet, then you just use your gravitation equation, right? So that's half of the shell theorem. The other half of the shell theorem is if you have another sort of hollow shell out here, what's the force of gravity on this due to this crappy shell that I just drew? Zero, right? Remember, anytime you're inside a shell, then your force of gravity is zero, right? So that tells us then, do you guys remember how to calculate? So if this is the Earth, solid Earth, and you're somehow in a little hole inside the Earth, there's you. Do you guys remember how to calculate the force of gravity on you there?
The ratio force. Like the Lars. Yeah, G over R squared.
Does that look familiar?
Yeah.
So I guess that's another one that isn't technically on your equation sheet. Whoa. Cool. All right. So I think those are all the main ideas. I don't know if that was helpful or not. Yeah. Okay. Good.
Do we need to know the velocity to put an object in a circular orbit?
Yeah, that was one of the ones that I starred. It's that V-circ equation that was back.
Okay.
You got it?
Yep.
Root GM over R, this guy? And again, honestly, every time I restart this chapter, I can't remember this equation. I know one of these equations has a 2, and I can never remember which one has the 2. If it's this has a 2 here, or this has a 2 on the bottom. So I always I just derive it just by setting this equal to mv squared over r. Like that's your safety net. And I've seen that question on, I think, 2 old AP tests derive an equation for the velocity of an object in circular orbit.
And that's just if the centripetal force is equal to the force of gravity. Okay.
Yeah. Okay. Other questions? Yeah. Not really. The only thing that we ran into with any calculus was that one where you had to find the force of gravitational attraction between an object and a rod.
Oh, yeah.
Oh,
Okay, and since then I've seen some where it's finding the force of gravitational attraction between a point and like a curved rod. So at some point we'll have to go back and do those. This one weirdly is easier than this one. Because your distance is constant, so that simplifies the calculation. But that's something I haven't seen on any of the old AP tests, so I'm not going to stress over it at this point. That's like one of those. Okay, what else, guys? All right, yeah, Jake.
Is this test gonna be almost just like the last one?
No, there's one FRQ. But it's one that I wrote. It's not an old AP one. It's like, I think, a pretty straightforward application of stuff that we've learned. I really tried to make it so that you didn't need your calculator a ton on this, so that it's, because I know like typing in all that scientific notation slows you down, so I really tried to make it, streamline it a little bit. I'm hoping it doesn't make it harder, but I think that. I've been doing 60-40, 60 multiple choice, 40 for the FRQ. I think so. Yeah, that seems like it's been working pretty well. I don't know. I'll tweak it next year, I'm sure, but for now it seems like that's cool. Yeah, Alex.
Just to clarify, the net energy of an object in orbit is negative?
Correct. I know.
I like that.
I don't either. I wish I had something more encouraging to tell you about that. It's really, it's weird. Okay. What else, you guys? Yeah, Francis.
So the E equals U over to the equals negative K.
Say that one more time for the what?
The elliptical. E equals U over 2 and E equals negative K. Is that, because I know for the net energy, you can replace R with A for ellipses. Can we also do that with those two? Because those are existing.
Yeah, those two equations you just spoke of are a reference to this, and that's only for circular. So yeah, the other equation that I didn't write here is this guy, E equals, what is it, positive U over 2. That is only true for a circular orbit.
So basically the only one we can use A with is.
Here's a really simple argument for how you can remember that. If you are in an elliptical orbit, then isn't your gravitational potential energy changing? So that would mean that your total energy was changing. See what I mean? And this is just a result of K plus U equals Z. So that's, I think that didn't register with me the first time I did the notes. This is one of those instances where I didn't realize, yeah. Are you good? Okay, really good questions. All right, what else, you guys? Okay, are there questions from the homework that have yet to be discussed? Last week when we went over stuff, we really focused on the forces part. I feel like we didn't focus too much on the energy stuff.
Is that what's going to be the majority of this class?
No, I think it's a pretty fair split.
Okay.
I mean, I tried to make sure that I hit each of the kind of big concepts once, which is, why I'm at like 15 questions right now. So.
Yeah.
Yeah.
Did you do 34 from 13.5?
Yes, 34 from 13.5. Oh, maybe I can.
Yeah, that one.
So focused on big concepts that I didn't grab my. Crossed. All right. Okay, 34 from 13.5. Graph number 29. Okay, yeah. Okay, so we've got a graph that looks something like this. So we're given Rs as an asymptote, and this guy goes down to -5, and -1 is up here, and then it kind of goes. Let's see, so what does it tell us? It says the graph in 29 gives us the potential energy, U, as a function of R. Here's R. Of a projectile plotted outward from the surface of a planet of radius RS, as in radius at the surface. If the projectile is launched radially outward from the surface with a mechanical energy of -2 times 10 to the -9 joules, what are the kinetic energy and the turning points? Got it. Okay, so I see. Okay, so what is this? This is all times 10 to the 9th joules. I'm going to add in a line that wasn't on the graph just to illustrate something. Okay, so here's the deal, you guys. The idea is, at the surface, we've got a very small amount of potential energy, right? It looks like, specifically, -5 times 10 to the 9th joules, right? So that's my potential energy at the surface, right? Okay. Now it tells us that our total mechanical energy is -2 times 10 to the -9th joules. So the idea is, we're launching it from the surface. So at the surface, our U is -5 times 10 to the 9th. Our mechanical energy is -2 times 10 to the 9th joules. So what can I right away figure out? The kinetic energy at the surface, right? -5 plus what is -2? Oh, well, 3. So there's my kinetic energy at the surface, right? Follow? All right, so wants to know what's the kinetic energy when R is 1.25 R. Well, that's just kind of graph reading, I think, right? So this is 1 R. By reading your graph, if you go over here to 1.25 RS, then you can find what your U is, right? And then subtract that from your total. Do I agree with that? Yes, I do. Because if you look, there are 1, 2, 3, 4 little boxes before RS. So each little box is a quarter of RS. Does that make sense? Good question. Alex?
Okay, so it says that the mechanical energy is that number.
Mm-hmm.
Does that mean that it is in a circular orbit?
No.
Why not?
Because it says it's being projected up from the surface.
So then why is the kinetic energy at that point negative E? Or I mean, yeah, negative, because wasn't it for like circular orbits that the kinetic energy is the opposite of the total energy?
Yes.
Is it just a coincidence that
It's not. The kinetic is 3 and the total is -2.
it says the answer is 2 times 10 to the 9th though?
Oh, I gotcha. Yes, that's just a weird coincidence.
Okay. That is,
I gotcha. Yeah, that's a total coincidence. So let's run through the calculation then, so you can see where that's coming from. So here's how they got that. Oh, well, whatever. Okay, so at 1.25 R, here's what you know. By looking at the graph, you can see that the potential energy is -4 times 10 to the 9th joules. Let me pause there for a minute so everybody can see how I got that. Everybody see that from the graph? Okay. And we know our E mechanical is -2 times 10 to the 9th joules. And so now to find your kinetic energy, it's just -4 plus what is -2. And it happens to be +2, which is an unfortunate coincidence.
okay.
Yeah, I can see where that would have thrown you off. Good, you guys? All right. And then to find the turning point, well, our turning point is going to occur when all of our energy is potential, right? Because that'll mean our kinetic energy is 0, right? And all of our energy is potential when the potential energy is -2, which by looking at the graph occurs at,
That point.
yeah, 2.5 R, it looks like, right? Because it's 6 little marks past R. Cool. Francis, you good? Is everybody good? Is anybody ungood? Dynamite. Right. So that's a good one because I think it stresses this idea that your total energy has to stay constant, and it exposes you a little bit to the weirdness of those stupid negative signs. Okay. Yeah.
31. I got the ratio for A, but for B, it says what is the value of the gravitational acceleration? It never gave me the radius, so I was confused how to do that.
Oh, gotcha. All right, let me say one quick thing about this before I rewind. I just want to reiterate, and this is something that Kurt pointed out when we learned this. Try not to let these negatives throw you out. This graph still has the shape you would expect even without the negatives, right? As you get farther away from the surface of the planet, your potential energy is increasing, right? Okay. All right. So 31. Let me see if that's going to be time well spent going over that one, or if it's just a bunch of algebra.
A was just a bunch of algebra. So,
Green folder, where are you? I left my notebook at home by accident. I was working over the weekend. Too much time fumbling around for it. Oh, here it is. Okay, which number? 31?
31.
B.
So gave you like the
Right. Shoot. I have an answer here where I used the...
no.
Oh, yeah, it gives you the radius.
Yeah.
Yeah. So it's literally just plug and chug. Do you see where it is? That's okay. Do you see why?
I thought.
Okay. Yeah, because it gives you the diameter of the planet, so you know your radius, you know the mass. So it's just plug and chug. Okay. That's okay. All right, what else, you guys? Yeah.
In 32, it says in problem 3, which one is problem 3?
I don't know why you were confused by that. Yeah, I'm sorry. So just so you guys know, the reason I'm using the random numbering system that I'm using is so that we can still reference the posted solutions that the textbook makers. That's why I haven't gone through and renumbered everything. One of these days I'll go through and, So that problem number 3 refers to textbook problem number 3, which would have been, the one on the...
Oh, geez.
Not question, but problem. So 13.1, number 3. I know, there's problems and there's questions. So the problems are like the problems. How else to say it? Sorry, I understand why that's confusing. All right, so what number was that again? 32. Let me see if there's anything there that is worth discussing right now. What's the gravitational potential energy? Oh, right, yeah. So that's just using the equation. If you triple the separate, okay, this is good. So what are some patterns, you guys? If you triple the distance, what's going to happen to the negative value of your u? It's going to be divided by a third, right? But keeping in mind that it's negative, that's actually getting bigger, right? Work. Remember, you guys, work is change in total energy, right? So if the question is about how much work do you need to do, like to get something into orbit, figure out how much energy you began with, how much energy you're going to need once you're at that point in the orbit, and find the difference. All right, so a couple of you guys came in and you expressed the fact that last week was just a wash. Here's the deal. I can't spend any more class time on 13. Okay? But if you guys said to me, I'd like another day or two to study, knowing that we're going to move on to chapter 15 tomorrow, is that something you guys want to do, knowing that that'll then put you behind on 15, or do you want to just do it and be done with it? Yeah? Yeah. Yeah, I don't think I'd want to move it much past Wednesday, because then we'd be doing 2 days of 15 stuff. Okay, let's do a quick vote. How many of you would rather do it? All All right, how many of you would rather do it Wednesday?
Wait, what are the options before?
What, Tuesday or Wednesday? Tomorrow or Wednesday? So these are Wednesday votes. 1, 2, 3, 4, 5, 6, 7, 8. That's clearly a majority. Okay. All right. So we'll do the test Wednesday. Tomorrow, then we will be starting 15. Okay. Good. If you voted to push it back because you don't know what's going on, I'm around before and after school. Come talk to me. All right. Okay. We're almost done. All right, have a good day, guys. Oh.